Hello and welcome back to chemistry. Today we are going to go ahead and cover acids and bases. We're going to go ahead and cover first the initial definitions, then we're going to go over the concept of conjugate acids and bases, and we're finally going to end up by discussing the strengths of different acids and bases. The first thing that we're going to need to do is talk about them and define them. Many of you have heard of acids and bases before, and many of you have either used them to clean or eaten them in some form or fashion. Any form of citrus is known to have some sort of acid, while most cleaning supplies involve some sort of basic solution. What we're going to first to define it is that we're going to go ahead and use a particular definition called the Bronsted-Lowry definition. And the Bronsted-Lowry definition states that an acid is going to be any species, and in this case it's species or chemical, which is able to donate a hydrogen ion into solution. Okay, and this is just hydrogen that has lost its electron, and it is able to release it into the solution. The hydrogen ion goes off its way. The other part of the acid does its own thing, and they're separated forever and they don't get back together. That's what an acid is. Whereas a base is going to function as the exact opposite. It's going to be able to absorb a hydrogen ion from a solution. And that's going to be the first set of definitions that I'm going to want you to make sure that you have down. Next here, I have an example. And this example starts with hydrochloric acid. Now, hydrochloric acid is just HCl, so it's a hydrogen and a chlorine, and they've been bonded together. And when hydrogen and chlorine go into solution, what happens is that the acid part, that H+, ends up wandering away. It ends up disappearing into solution and release that hydrogen ion. Whereas that chlorine is going to have a nice negative ion there, and it's going to also be in solution. HCl is considered an acid because it releases hydrogen into solution. The second type that we have here is called acetic acid. And acetic acid, notice that it's CH3COOH, is also an acid. Even though it has an H in the back instead of the front, we still consider it an acid because, as you can see from the equation, it loses a hydrogen ion once it goes into solution. So that makes it an acid. Next, we have an example of a base. Now, this is a very strong base. This is a base that's called sodium hydroxide. And when sodium hydroxide dissolves into solution, what will happen is it'll end up losing its sodium ion. Its sodium ion will stay in that water. It'll be floating around there and it won't do anything else. And the OH ion, the hydroxide ion, is actually going to go ahead and absorb some hydrogen from the surrounding areas. So that's what we mean by this as being a base. It's actually going to absorb hydrogen. It's going to take it away from somewhere. So that's what a base does. It absorbs. Now, when you have an acid and a base, we like to say that they make conjugate base pairs. So right here, this is an example of a conjugate base pair. On the left, we have acetic acid, which is the CH3COOH, and that's able to release a hydrogen into solution. And on the right, we have the conjugate base. And this conjugate base is able to absorb a hydrogen. Okay, So this conjugate base in this case is called the acetate ion. This acetate ion could theoretically absorb the hydrogen and put it back into acetic acid. And when we say conjugate acid and conjugate base, all that we're looking for is we're looking for the opposite. So if it's a conjugate acid that we're looking for, that molecule should be something that has one more hydrogen attached to it in some way than the one before. Likewise, if we're looking for something that's a conjugate base, that's going to be something that has one less hydrogen ion attached to it. Notice also that the charge between the conjugate acid and the base has changed. In the case of the acid, it has gone from a neutral compound to one that has a positive or a negative charge to it. Okay, and that's because that hydrogen ion has left behind its electron. Likewise, when it goes from base, it goes back to a neutral compound because it gains a hydrogen ion and it balances out that charge. This can be shown even further here with a more complicated one. This right here is an example of H2SO4. And H2SO4 has a couple of different states because it has both of the hydrogens to start with. It can gradually lose both of those when it goes into solution. So when we first put H2SO4 into water, what will happen is that it will lose that first hydrogen, and that first hydrogen will go into solution. And it'll also make the conjugate base for H2SO4, which is HSO4 minus. So in this case, the acid is H2SO4, which is known as sulfuric acid, and the base is HSO4 minus. So the conjugate base and the conjugate acid to that base, those are both conjugates of each other. Now we have another set where that HSO4 minus also has the ability to lose another hydrogen ion. And when it does that, it'll be just the hydrogen ion and the sulfur ion. Notice that it is now at a 2- charge. Okay? That conjugate base has lost one more hydrogen ion than the acid before. So in this case, the HSO4 ends up being an acid because it loses a hydrogen ion. And its conjugate base then ends up being the SO4 2 minus. Okay. The last thing that we want to talk about is strong versus weak acids. Okay. You already know that different things dissolve and different things react at different rates. And the same goes for acids. Different acids are going to lose that hydrogen ion at different rates when they're in solution. Likewise, they're going to absorb that hydrogen ion at different rates in solution. The speed at which they are able to do that determines the strength of the acid or base in this case. Now, the following is a whole set of rules that help to determine how strong an acid or base is going to be. And we're going to go ahead and go over them each individually to help you conceptualize them here. But this is just the basic rules to determine how strong an acid is going to be in comparison to others. So the first rule has to do with the conjugate base. If the conjugate base is not very good at absorbing a hydrogen, then it's going to be a strong acid. So, for instance, right here, let's say that the acetate ion was not very good at holding on to hydrogen. It would end up being a strong acid then because of that. Now, in this particular case, acetate ion is fairly good at holding on to hydrogen. Since it is good at holding on to hydrogen, it means that this is going to be a weak acid. The second rule that we use to go ahead and help determine the strength of an acid has to deal with periodic trends. So, and this especially works with a monoprotic acid, that the strength of acid is going to increase as you go across the row. So as you go from left to right, it's going to increase in strength. And then as you go down the table, it's going to increase in strength as well, which means that hydrobromic acid will be a stronger acid than hydrochloric acid. The last one, we have oxygen attached to it. So what some of our polyatomic ions, and in general, as you increase the size of the atom that's in the middle. So for instance, if you had phosphate versus arsenate, okay, phosphate is going to go ahead and be smaller than arsenate. Therefore, it's going to be a weaker acid than the arsenate is. Okay. So the bigger the central atom, the atom that's holding on to all the oxygens, the stronger that acid is going to be. Next, the more oxygens that you have around it is going to end up increasing the strength of the acid. So in the case of sulfate, which is O4, versus sulfite, which is SO3, since the sulfate has SO4 and more oxygens, it will end up being a stronger acid. Okay. Those are the rules for how to determine how strong an acid will be. And with those rules, you'll now be able to go ahead and work on the worksheet for tomorrow, which will go ahead and go over how to choose a strong acid, determine a conjugate acid and base, and rank acids in terms of increasing strength. Thank you and have a good evening.